Thanks for having me. My name is Adam Peterson. I work for the CCSE group. And today I want to share with you a problem that I actually conducted in my previous life as a pure theoretical physicist at the University of Toronto. The reason for this is that it kind of inspired my employment and interest in working for the CCSE group, and also kind of has inspired some new projects which I'll share with you at the end of the talk. Anyway, the title is The Numerical Construction of Vortices in a Strongly Coupled Superconductor. So let's start. So I'll just start with a little bit of motivation about this problem, why it's interesting, where it comes from. I'll give a brief introduction to the holographic principle, the ADS-CFT. Not a very large one, just a simple one because it's kind of crazy. I'll talk a little bit about superconductors and the properties that interest us. I'll go a little bit into the computational approach. I know I'm talking to a computational group, so they're going to be disappointed that there's only 2 slides on it. But that's, I hope I can get the point across. I'll talk about the solutions we constructed, the actual vortex solutions, the thermodynamic analysis, and then I'll finish with the actual, interesting part, which is where we're going to go with this project. So this problem stems from the biggest notorious overarching problem of theoretical physics, which is the strong coupling problem. By that I mean any problem that can't be simplified by first solving a well-known problem and then slightly changing it. And instead, in a strongly coupled problem, you kind of more or less have to solve it all right away, either analytically, non-perturbatively. There's no building up to the solution. You either know it or you don't. However, there are some techniques, there are some things that theorists have built over the years. One of them is the holographic principle, which actually describes strongly coupled systems by relating them to corresponding systems in a gravitational system. So I'm going to use it today to describe vortices in strongly coupled superconductors, just like my title. But in particular, the actual addition that we've included in this problem is we're going to add some degrees of freedom to the vortex. And the reason for this, it provides insight on the confinement mechanism in QCD. I don't know how many of you are aware, but one of the principles of QCD is quarks and gluons are never observed in isolation. They always come in either pairs or triplets or groups, and the reason for this is the confinement mechanism. And our hope is to at least take a step in that kind of unsolved problem. Okay, so as I stated at the beginning, the ADS-CFT and the holographic principle is a very esoteric part of theoretical physics. It comes from string theory. So I'm not going to be able to explain the whole thing here, but the picture I kind of want to put in your head is the idea that we're trying to describe a 2-dimensional system, a highly quantum, strongly coupled 2-dimensional system, which corresponds to a 3-dimensional system in Einstein's gravity. And roughly the idea here is if you solve your 3-dimensional system and look at what's going on at the boundary of your 3-dimensional system, you can actually deduce information about your 2-dimensional quantum system. So in other words, we're trading the complexity of quantum mechanics for the complexity of Einstein's gravity. And the benefit there is at least Einstein's gravity is a classical system. It's still complicated, but at least you can put it on a computer. Okay, now, with that in mind, I want to talk about superconductors real quick. And the property of superconductors I want to talk about is actually the Meissner effect. So in your standard, so what I have pictured here, you've got a thin superconductor in which we're looking at it edgewise here. And the superconducting property is something known as the order parameter. And basically what that means is that if the order parameter is non-zero, a system is superconducting, and when a system is superconducting, it expels all magnetic fields. Okay? However, we're interested in something known as a type 2 superconductor, which actually allows some magnetic field to penetrate through vortices within your superconducting material. So the way that works is that you have your superconducting material, which mostly your order parameter phi is non-zero. However, there's some localized regions where the magnetic field can actually penetrate through the superconductor where phi goes to 0. I'll go a little bit into how that works in a couple of seconds here. So putting these two things together, what you should envision is we have a vortex that's living in our three-dimensional space here. I gotta stay here. Oh, shoot. Okay, I can use this, right? Okay, so we have our vortex that's living in a three-dimensional space. And so that's what we're going to try to solve for classically. And we're going to look at so there's two vortices. There's a 3D vortex and a 2D vortex. The 2D vortex is the vortex we're interested in. I hope I'm not losing everybody. I gave this talk before, and whatever. So we're interested in the actual 2D vortex that we're going to construct by solving a problem in three dimensions, okay? So you can kind of see the similar things here. You got your order parameter phi is non-zero away from the vortex, and near the vortex it goes to 0, okay? Also, the equations I've put up here are two sets of equations. Some of you may recognize the first one, that's Einstein's equation. It looks kind of cute. And the other one is the equation associated with the order parameter, okay? And so that's all nice, but what we actually want to do is we want to add a little bit something extra to this system. We actually want to make the vortex core superconducting itself by adding another order parameter that will hopefully be induced within the vortex core. Okay, so this is going to be what represents our additional degrees of freedom in our final solution. Okay, so I've written down those cute equations. They look pretty, right? Like they're not too terrifying. Oh shoot, sorry, I missed a slide. Before we get to that, we must solve Einstein's equations with two order parameters, phi and chi. The field depends on a radial direction r, the distance from the core, as well as a holographic direction, which represents the dimension this dimension, the dimension that flows away from the 2D surface. The metric for Einstein's gravity has 5 undetermined fields for the system we're describing. I didn't write it down, but we also have an electromagnetic field. Of course we do. We've got a magnetic field. And then finally, we have the additional, I already described the order parameter. So in total, we have 8 fields to solve for. And as I started to say earlier, the symbolic form makes it look reasonable. But this is one part of one equation that we wind up with, okay? So I was told not to show this slide because no one's going to be able to absorb it, but I kind of argued that's the damn point. Like, you're not supposed to absorb it. Instead, we're going to need computer algorithms to actually organize this equation for us. So that's what we actually do. And you know, there's lots of solvers out there. The one we used was Mathematica, in which we actually wrote a code that took this equation, organized it, linearized it, and performed a recursion method on it. It's just Newton's method to solve the system. In addition, since at the time we didn't have access to these really nice, supercomputers, we just had our laptops. We had to find a way to simplify the grid. We can't use a 256 by 256 grid anymore because we just simply don't have the computing power to do it. So we used a Chebyshev decomposition to reduce the number of points that we actually need, because Chebyshev polynomials are really good at representing relatively smooth functions. So you can get away with fewer points when trying to describe, when trying to discretize a system. So instead of, like I said, 256 points, we can get away with like 20 or 40 grid points on our domain. So at the end of the day, we have 8 fields, and 40 grid points in each direction, the holographic and the radial direction. So it leads to a 12,800 component linear system that we have to solve for. But at the end of the day, it looks cute. It's just, your standard linear solver. It's just LV equals B. You just got to invert L. Computers are good at that. So like I said, I'm kind of glossing over the computational part. I'm going to go straight into solutions. So like I said earlier, this is, if we're solving for a vortex without any additional field attached to it, this is representing the field phi as we look at it on the boundary with respect to the radial direction. you can see as we get further from the radial direction that the field kind of returns to its vacuum expectation value, the value of the field it wants to be in its ground state. But of course, as we get closer to the core of the vortex, it goes to 0, just like expected. Order parameter goes to 0, magnetic field can penetrate this point. So what we want to ask is, does it want to be in this configuration where there's nothing going on in the core of the vortex? So we perturb it with by adding a small amount of the field chi, and we just see what it wants to do. And we actually find that the chi field does indeed want to develop in the core of the vortex. It seems to be the preferred state of the system. And so in other words, a vortex with additional degrees of freedom it appears to be the preferred configuration for the system. So that's interesting. We can confirm this by actually looking at the thermodynamics of the problem. We can look at the free energy with a chi field versus the free energy without a chi field, and we can ask, which one's greater. And it turns out the free energy with no chi field is greater for the temperatures. Excuse me, I forgot to change. YH is just proportional to the temperature of the system. Okay. So we find that since also physicists like to do this. Kappa is -1, so everything's backwards. But what we're finding is that the case with no chi field has a higher free energy than a case with additional degrees of freedom. So that means the case with additional degrees of freedom is actually thermodynamically preferred for the temperatures we're considering. So we can go a little bit further. We can start to ask, okay, so now we have a single vortex. What happens if you add multiple vortices to your sample? And so like I stated earlier, there's two types of superconductors. There's a type 2 superconductor in which if you add more vortices to your system, they actually want to repel each other. Okay? So that means as you increase your magnetic field, more and more vortices try to enter the system, but they're repelled from each other, so they form a lattice instead. And so instead of the field or the magnetic field or the superconducting, instead of the order parameter being destroyed, the magnetic field can kind of slowly increase in the superconductor by adding more and more vortices. The more conventional case is a type 1 superconductor in which vortices want to attract. So if you have two vortices that enter your system, they want to come together and form a single n=2 vortex. So what that means is that as you reach a critical temperature, all the vortices just, they inundate the system and they form one giant vortex. In other words, the entire magnetic field is just, or the entire superconducting property of the material is destroyed. Okay, so we can ask the question, for different charges of our vortex, which state does it prefer to be in? And so the way we did that, we actually asked, we took the free energy of a single vortex and compared that to half the energy of a n=2 winding vortex. And that simply tells us, which is lower free energy, 2 single vortices or 1 double vortex. And we found for lower charges, it actually prefers to be a type 2 vortex in which the vortices prefer to be in the single vortex configuration. It means they repel each other. However, for Q=2, we get the opposite behavior. Vortices prefer to be in the, they prefer to combine into a single higher winding vortex. Okay, so that was the kind of the conclusions of the work we did. Just to summarize, we have solved Einstein's equations on a holographic superconducting vortex. We have introduced additional degrees of freedom in the core of the vortex. We have found that the additional degrees of freedom are thermodynamically preferred, and we also were able to determine some of the type behavior, whether it wants to be a type 2 or type 1 vortex, depending on the charge of the material. Okay. So just going on to a little bit of what the future of this project might be. This problem provides insight into holographic superconductors and related problems in high-energy physics and cosmology. It also highlights the effectiveness of current computational methods to tackle deep theoretical problems. And by that, I mean, like, we solved it on our laptop. We didn't use any supercomputers. So, yeah. And so one of the things is this might lead to a more satisfactory description of the confinement mechanisms in strongly coupled theories. Okay, I have a few more minutes. Oops, sorry. Where was I? Okay, so like I said earlier, me presenting this problem actually was what inspired my working in this position at LBL. This project has inspired a continued effort at LBL to expand the reach of scientific computing to deeper problems in theoretical physics. So one of my current projects is actually developing an interface between Einstein's equations in symbolic form and unpacking them into something that a numerical solver like Amrex can use. At the moment, this is the interest is people trying to solve systems of neutron stars and black holes. But what I think is that this can actually be useful for a problem in theoretical high energy physics if you can relate that problem to a holographic system somehow. So in that regard, there are few problems to overcome. Currently, the only formulations of numerical relativity are the what are known as the 3+1 ADM and variants of that system. So it kind of constrains the coordinate system we're allowed to use for Einstein's equations. So either we have to find a way to write the problems in this D+1 formulation, or we have to develop an expanded set of numerical approaches that can deal with holographic problems. In addition, the world we live in is clearly 3+1 dimensional, three spatial, one time. So if we want to describe our highly quantum universe in a holographic way, we're actually going to need to go to 4+1 dimensions in our holographic system. Okay. And finally, we're going to have to determine a configuration of monopoles and vortices in holography that corresponds to the behavior of confinement mechanisms in QCD. One of the problems in holography is actually finding a configuration for your gravitational system that actually corresponds to the quantum system you're really interested in. Okay. All right. That's it. Thank you. Yeah.
So I realize that maybe I understand a little bit of things, but probably nothing. So I don't even know what you're solving for. Is it a steady-state solution of something?
Yes. It's a steady-state vortex.
Steady-state vortex. Okay. So and the two dimensions are radial and away from this 2D plane.
Can you repeat the question?
Sorry.
Just so for the mic.
Oh.
Repeat the question from the mic.
Oh, so he's asking me what are the two dimensions I'm referring to, and I'm gonna make it worse for him because in the 3D problem, the three spatial problem, the vortex depends on two coordinates, the radial and the holographic direction. The system we're trying to describe actually lives on the boundary of that space, and since it's a two-dimensional boundary of the three-dimensional space, so the two sets of two dimensions are, in fact, distinct from one another. Yeah.
So when you have the order parameter 5, right? I know there's probably like multiple levels of abstraction before you get there. But like, is there anything in a physical, like if I have a 2D semiconductor, like if I have a 2D actual material, what's the closest physical thing to that?
So we've certainly got like a very thin superconducting materials in which you can approximate them as 2D systems. Reason why we're doing a 2D system here is because it's just simpler. The whole paradigm of theoretical high-energy physics now is simplifying the system so much that it hardly resembles the real world, but at least you can get some ideas of what might be going on in the real world.
So is there anything physical that this phi is close to?
Yeah, of course. So I don't know how much you know about superconductivity, but in a weakly coupled superconductor, it quantifies the density of Cooper pairs. Does that help? Yeah. Yeah. Okay. So it's the interaction of electrons that form the Cooper pairs that introduce the superconductivity. So yeah, that's yeah.
Sign error. But you use this Chebyshev expansion to reduce the dimension you have to solve for. That implies a certain smoothness to the system, which then implies a certain simplicity to the problem you constructed. So I'm kind of curious if you were to sort of move this to a much larger, say, supercomputing system, where you can go to 56 squared or something, and even or higher moments of the Chebyshev thing. Can you get a sense for what you would gain in your ability to what additional complexity would buy you in this problem that you could represent?
So one of the paths we want to take with this is so we've got this vortex that has these additional degrees of freedom, which represents quark interactions in the confinement mechanism. What we would like to do is actually start asking the question, can we come up with configurations that more closely resemble that confining behavior? A single vortex is cute. It shows that additional degrees of freedom are actually the preferred state, but we haven't actually shown like how do two vortices, for example, interact with one another. And so as soon as you add a second vortex in the system, you've already broken the axial symmetry of your problem. So now you've already got now you've added a third dimension to your problem, and most certainly you'll start to lose the smoothness behavior of your system. And so yeah, that would be one of the reasons why we'd be interested in kind of, the Chebyshev is so cute, but we will have to abandon it eventually if we. Yeah. Does that answer your question?
Yeah. I think in your last slide you mentioned that you can use this approach is using solving strongly coupled systems using this holography method, and QCD is an important strongly coupled system. So you can, if you can formulate the right to get into the other space, you can actually solve QCD. Is that the claim?
No. So as I forget who asked, I said something about theoretical physicists like to simplify a system. Right now, holography only works for problems that are holographically compatible. And QCD is definitely not holographically compatible, partially because it has a mass gap. You need a conformal field theory for it to actually work, which means you cannot have any scale constants or masses in your system. So no, it's not going to provide a solution to the confinement mechanism in QCD. What it might do for us is it might tell us a little bit more about some of the qualitative characteristics of how confinement works in QCD. But yes, you've called me out. It won't solve QCD.
So that is QCD people their time is worth it.
Yes. Yeah. They're not. I'm no threat to them. So.
Do you have any intuition about how adding degrees of freedom in like a ADS5 vortices set up, what that would actually correspond to in like a confinement?
That is a
physics?
good question. That's a good question. We should talk about that afterwards because I don't think I can answer it here. Sorry. Yeah.
Does the boundary of your domain have to be flat or just a restriction?
It's a restriction for this problem because the superconductor you're trying to describe should have a translational invariance, which you only achieve in a flat space. Actually, that's not really true. It is flat, but it does not have to be flat. What you do need is you do need your system to relax to an ADS configuration. So it has to. There are some constraints, but it doesn't necessarily have to be flat.